and became a faculty member at Jadavpur University Physics Department. So he was the teacher in more than one person in this room now. So Dr. Ratnakule and Dr. Shamadip Shami, they were students at Jadavpur during that period. And then he finally moved back to Calcutta University as a faculty member, where he has been since then. And Professor Kundu has written more close to 100 papers in various research journals, and close to, I think, or more than 10 PhD students have gotten their PhD under his guidance. He is the fellow of the National Academy of Science and the Indian Academy of Sciences, and his research is in particle physics, in also some application to astrophysics, and I think Higgs field and those topics were always part of his work. So we eagerly wait to see his talk on this one.
Thank you, Ritavan, for this kind introduction. And of course, it is always very special to be here in Presidency. As Ritavan said, I did my undergraduate from Presidency. At that time, it was only the physics department. There was no school of astrophysics. It was a college under Calcutta University. It was not a university. And there was no such mezzanine floor, but it was still Presidency. Okay, so I think I have to use this, right?
Yes.
Okay, fine. Okay, so as you have seen, the title is some unanswered questions about the Higgs boson. I'm sure you all know about the Higgs boson. So before I go into the unanswered questions, first let's see what are the questions that are already answered. So first I will show, again, this talk is essentially for the master's level students and not for the more senior people. So for the more senior people, you can just fall asleep if you want. So the first, we will see why we need the Higgs boson and what is the standard model Higgs boson. And then, okay, which one? Oh, okay. And then, okay, this is a very select list of some of the unanswered questions. And I probably will not have time to touch all of them. So for example, the first question that is still unanswered is why the Higgs is so light. Of course, you will say that Higgs is not light. It is about 125 GeV. It is almost as heavy as a gold nucleus. But we will see what I mean by a light Higgs, and also how that affects the stability of our universe where we live, which in technical terms we call the vacuum. Then, of course, there is a possibility, a very interesting possibility, that the Higgs may interact with the dark matter. We know that the other particles of the standard model, they do not interact with the dark matter. That's why it's called dark. But there is always a possibility that Higgs might be the one thing that talks with the dark matter. And we will also try to say a few things about the role of the Higgs in the early universe phase transition. Of course, I will try to tell you what I mean by this early universe phase transition. And then comes the most interesting question as far as the experimentalists are concerned, whether there is only one Higgs or whether there are brothers and sisters of Higgs.
So, Anirban, in the beginning, by Higgs boson as a rescue, you meant that it was predicted in the standard model, but it was not observed, but then finally it was observed?
No, by rescue, I mean why it is at all needed for the weak interaction. See, this part again, of course, is only for the younger people. So, you know that the electricity and magnetism, they had their own laws. So, they were sort of disjoint things. But then came this guy, Maxwell. He showed that you can unify all of these laws into some compact framework. And in fact, what he did, it's not just that he predicted that there should be a term like this to make all these things consistent. What he did is that he unified three completely uncorrelated things at that time: electricity, magnetism, and light. He showed that the information goes from one point to another in the form of electromagnetic waves, and electromagnetic waves travel with the velocity of light. Remember that the velocity of light was measured earlier by Olaf Romer and other people. It turned out that you can express the velocity of light in terms of this constants mu0 and epsilon 0. That's a good thing. So we know that we can express the electric field and the magnetic field in terms of scalar and the vector potentials. Of course, we cannot measure the potentials. We can only measure the electric and the magnetic fields. Okay, so I have the freedom to change the scalar potential as well as the vector potential in this way by introducing some term like this. This is called a gauge transformation, and it is very easy to check that this transformation keeps E and B invariant. So that's what is called gauge invariance. And gauge invariance is a necessary and a sufficient condition for the conservation of electric charge. Of course, we know that the electric charge is conserved in every interaction, so gauge invariance is a must. Now, we know that when you quantize the electromagnetic field, we get some excitation of the field, which we call photons, and the photons are massless because the electromagnetic field has an infinite range. So the question is, can I write a mass term for the photon? I know how to write a mass term for the photon, but if I write that, unfortunately, I don't have a blackboard here, but anyway. Then,
it's whiteboard. So
anyway. If I try to write a mass term for the photon, it is easy to show that that breaks gauge invariance. So that's a very bad thing, but fortunately, photon is massless, so everything is fine. So that is the crucial point, that if you try to write a theory like electromagnetism, the force carriers, the spin one objects that carry the force, they must be massless or the gauge invariance will be broken. Now let's come to the weak interaction. So let's first talk about the fermions. Fermions are spin half objects, so they can have spin plus half or minus half. I mean, on some axis, the projections are plus half and minus half. So let's take the momentum as the axis. So it can either be along the direction of the momentum, or it can be anti-parallel, so that this operator sigma dot the direction of momentum, this can either be plus half or minus half. For historical reasons, we call these plus half objects as the right-handed objects and the minus half objects as the left-handed objects. Of course, here, if you have already learned about relativistic quantum mechanics, you know that I am slightly cheating in the sense that actually the right and the left-handed objects are obtained with the application of the matrix gamma 5 that you encounter in Dirac theory. But if I take the electrons to be massless, it is an equally good definition. So there are two types of electrons, right and left. The good part about electrodynamics is that this does not differentiate between the right and the left electrons, and that's why in your BSc days, you have never heard about right or left. But it's not so for the weak interaction. For example, we can look at the beta decay, a neutron decaying into a proton and something called an electron and an antineutrino. Now, these objects, they are massless. They do not have any electric charge. They are leptons, so they do not have any strong interactions. So the only thing that they can feel are the weak interactions. So in any process, if you see some neutron, you know that it's weak interaction. So people try to measure the handedness of the neutron and the handedness of the electron that comes out in weak interaction. There was this famous experiment of Madame Wu and also by Maurice Goldhaber. This is a very beautiful experiment. So if you have time, just go through this paper. This is completely understandable by any undergraduate student, and it's a beautiful application of simply momentum conservation to get the angular momentum of the neutron. Okay, the main point is that weak interaction involves only the left-handed factors, not the right-handed. So the weak interaction does not see the right-handed objects. So now, if I ask the question whether we can have a gauge theory for weak interaction like electrodynamics, the first point is that I need 3 such weak photons. 3 such weak photons because electrodynamics does not change the charge of a particle, but weak interaction does. So I need 2 charged objects, a positively charged and a negatively charged object, which I call W plus and W minus, and a neutral object, which I call Z. So if I use a group theoretic jargon, for those who know something about group theory, electromagnetism is the local gauge theory, which is described by a U1 group, and weak interaction again is a local gauge theory, which is described by SU2. The only difference between SU2 and U1 is that U1 is abelian and SU2 is not abelian, but these are technical terms, so let's not go into it. The important point is that this will have 3 such gauge bosons and U1 will have only 1, which is the photon. Also, weak interaction is very short range, it does not go outside the nucleus. So the carriers of the weak interaction, they cannot be massless, they must be very massive. You can even calculate the mass from uncertainty principle. And also the left fermions see the weak interaction and the right fermions cannot. Now these 2 facts, when you combine them, it tells you that if you really want to keep the gauge invariance, you are in a soup, because if you want to keep the gauge invariance, these objects, the W plus, W minus, and Z, they cannot be massive. And it can also be shown that even the fermions cannot have a mass time. Now that's very bad. We know that these objects are massive. The fermions, of course, have some mass. We have measured the electron mass. So the thing really looks very bad. So now,
so these L-fermions can see and R-fermions can, is that known?
The violation thing. That is the handedness violation, right?
No, see, the weak interaction, since you have, if you look at the Lorentz structure, this involves some 1 minus gamma 5. And 1 minus gamma 5 means when it hits the right-handed wave function, this gives you 0. Okay. Now we heard that there are 4 fundamental forces: gravity, electromagnetism, weak interaction, and strong interaction. But these 3 gentlemen, Sheldon Glashow, Steven Weinberg, and Abdul Salam, they showed that electromagnetism and weak interaction can be unified. So this was another case of unification after Maxwell. And this combined theory is known as the electroweak theory. So what they proposed is a theory that involves both electromagnetism and weak interaction. So the combined theory is valid at some high energy scale, and at the low energy scale, the electromagnetism part and the weak interaction part, they branch off. So we have a complete package of strong interaction. Strong interaction is not unified with this. People are still trying to unify the strong interaction with this, but they have not succeeded. And forget about gravity, because there is no quantum theory of gravity. People might claim that there are quantum theories, but just forget about those claims. No one has quantized. Okay. The point is that this complete package, strong interaction is also another gauge theory. But fortunately, the strong interaction photons, I mean the photon analogs of strong interaction, they are massless. So you are safe there. This complete package is known as the standard.
Only one that.
Yes.
So, strong interaction is also short range, very short.
Oh, that is because of another reason. That is because of your, I mean, the non-abelian nature, which prevents the colored objects to go further
That's
apart.
that's the confinement.
That's the infrared sliver confinement. Okay, so this works if and only if there is a Higgs. And let me show you how. Okay. So this is a very colorful picture of the standard model. I sometimes call it the colorful standard model. So see this, see what I mean? We have 3 generations of fermions. We have 6 quarks up and down. And in the first generation, we have the electron and its corresponding neutrino. Then I have the second generation. The particle physicists are very unimaginative sometimes. Sometimes they're very imaginative, sometimes they're very unimaginative. Now, this is called charm and strange. This is called strange because when this was found in mesons called strange mesons because they behaved in a strange way. So fine, they call it strange. And this one is called charm. And the corresponding leptons, that I mean the big brothers of electrons, are called muons, and this is corresponding neutrino. And then we have a third generation. Americans call it top and bottom, just like typical Americans. Europeans are better, they call it truth and beauty. But since science is ruled by the Americans, these names. And these are very heavy leptons. I mean, the really big brother of electrons. This is called the tau lepton and its corresponding neutrino. Tau lepton is even heavier than the proton. Okay, and then I have the antiparticles. Now, why do I have three such U's or 3 such D's? That is because they take part in strong interaction, and you can show that objects that take part in strong interaction, they can come in 3 different forms. These are called colors. Of course, this has nothing to do with ordinary colors. Anyway, I'm not going to that. And then we have the carriers of the strong interaction. There are 8 such objects. They are called gluons. They are massless. Then I have the photon, then the W, the 2 W's and the Z, and the Higgs boson. So that's the complete zoo. So now let's see what the standard model Higgs boson is. First, let us assume you have all read about quantum mechanics. Suppose you have a potential which looks like x squared. So this is a harmonic oscillating potential. So if you look at the Lagrangian is symmetric under x going to minus x. That if the Hamiltonian commutes with parity, then of course the states, your ground states, they will also be eigenstates of parity if this is non-degenerate. So both the Lagrangian and the ground state, they are symmetric if you change x to minus x. Suppose you have a potential that looks like this. This is an explicit breaking of parity. I mean, explicit breaking of x going to minus x. So you don't expect your ground states to be eigenfunctions of parity. But then look at this third potential. See the Lagrangian, this is symmetric if you change x to minus x. But if you look at the form of this potential, you can just, I mean, all of you have mobile phones and you can easily plot this. You will see that this looks like this. Comes down, goes up, comes down, and then goes up again. And so this is 2 local minima and 1 local maximum, and the local maximum falls at x equal to 0. So x equal to 0 is not a stable. X equal to 0 is an unstable point. The theory must come down to the stable points, the vacuum, and this, it can either come down to the left side or to the right side. Of course, my left and my right, for you it is the other way around. And this is called a spontaneous breaking, where the Lagrangian is invariant under some symmetry, but the ground state is not. So a very good analogy of spontaneous breaking is like this. Suppose you people went to a restaurant and there's a big circular table and you all sit around this table. And the waiter comes and he puts the glasses just between two of you. So everyone will have one glass on the right hand side and one glass on the left hand side.
All containing water. Right?
All containing water. This is a perfectly symmetric situation. Now suppose your AC madam feels thirsty and she picks up one glass. Say she picks up the glass on the right hand side. Now once she picks up the glass on the right hand side, this is a case of spontaneous breaking. She could have picked up a glass, either the left one or the right one. But once she picks up the right hand glass, every one of you must pick up the right hand glass. Otherwise, what happens is that someone will have two glasses and someone will have no glasses. That's a very bad. Okay. So this is how she breaks the symmetry. And once she breaks the symmetry, you all go to that configuration. Okay, sorry. I have to use this. So the mechanism goes like this. This mechanism was proposed in 1964 by 6 people. But generally it is known by the name of 3 of them, Brew, Unanswered, and Higgs. This goes like this. Suppose you have a complex doublet scalar field, doublet under SU2, so that this looks like this. This has 4 degrees of freedom. These are all real fields. And you can show that this has electric charge +1, these are electrically neutral. And the potential looks like this, with mu square and lambda greater than 0. But this is exactly like this. So if you have this, the 0, the origin is an unstable equilibrium. So the configuration will break the symmetry spontaneously, and what happens is that the fields roll down, say here. It could have rolled down here or here or here. This is a spontaneous breaking of the symmetry. Suppose it rolls down here. So, and this is called a vacuum expectation value. This is the expectation value of this operator. Remember that in field theory, if you take the expectation value of a single field, this should be 0 because of the properties of the vacuum. But now we have shifted the vacuum. So the vacuum expectation value is something non-zero. But once you do this, you get a mass term for the Higgs, which is given by this. And this is a spontaneous breaking. The original group was O4. I have 4 fields and it was a completely symmetric configuration. But now one of these fields have developed a vacuum expectation value. There are only 3 remaining. So the group O4 breaks down to O3. Now this vacuum expectation value you can calculate, and this is related with the Fermi constant. But we know the value of the Fermi constant. So this tells you that the vacuum expectation value is something like 250 GeV. And that tells you that this coupling lambda, this is called the Higgs self-coupling, and this will play an important role in our discussion. This coupling lambda, which goes with something like 5⁴, this you know the value of this. This is something like 0.13. How do I know this value? Because people have measured the Higgs mass. Once you have this mass, you just use this expression and you get this value. Okay. So what happens is that after you break the symmetry spontaneously, you have only one massive field remaining in the spectrum, and this is called the Higgs boson. Note these 4 lines. These 4 lines. And that is why this is called the Higgs boson and not the Brew-Unanswered Higgs boson. Because only in the paper of Peter Higgs, this is a PRL paper, and for those of you who will be told by your teachers that you have to write a fat paper to get published, remember that this is a paper that gave him the Nobel Prize. This is a PRL paper of 1.5 pages. 1.5 pages, and this was the last paragraph written very apologetically after the comments of the referee, where he said that once you break this symmetry in the spectrum, you may have a scalar. And that is called the Higgs boson, and it is this line that gave him the Nobel Prize.
Or maybe the name, probably, the Higgs name.
Also the name.
So the others also got
The name, of course, was not given by Higgs, that was given later on by someone called Benjamin Lee. Benjamin Lee died in a car crash. So that was a very tragic accident. It was on some
Fermi level এনেছিলেন?
Fermi level. It was on some
1980s.
it was on some American road. Ben Lee was
Joglekot.
exactly. Joglekot was in the next
In the
car.
next car.
Joglekot was in the next car.
Looked up at that time of India.
Anyway, okay. So what happens is this: you write the kinetic term of the Higgs. This is the covariant derivative for the Higgs field. This involves a term like this, but you give this a vacuum expectation value like this. So this develops a mass term. And see that you have not broken the gauge invariance in any way. You have just developed a mass term because of the spontaneous symmetry breaking. And you follow the same mechanism for the fermions, and you develop a mass term, psi L bar psi R times some constant. You develop a mass term for the fermions. You have not broken the gauge invariance in any way. Now that's the
That
beautiful.
was the rescue.
Yes, that's the beautiful thing. That's the beautiful. So let's see what the other good properties are. The standard model is a renormalizable theory. What do I mean by a renormalizable theory? A renormalizable theory is a theory where if you try to calculate the quantum corrections are manageable. In general, when you do calculations in a quantum field theory, some things come out to be infinite in every theory. So you have to apply some prescription to remove this infinity. A renormalizable theory is a theory where if you remove these infinities, say from 2 or 3 objects, then you can work with the rest of the theory and you will never encounter any infinity. A non-renormalizable theory is a theory where you have to remove the infinities at every order of perturbation theory. Quantum calculations are essentially perturbation. Every orders of perturbation theory, so you cannot get anything meaningful. This is a renormalization. And Higgs boson plays a very important role in the renormalization. That was shown by these two gentlemen, Martinus Wertmann and his student Gerhard Hooft. They got the Nobel Prize again. Now, this means that when you look at the scattering of gauge boson, suppose you are looking at the scattering of a W plus with a W minus, going into a W plus and W minus. You can draw all sorts of Feynman diagrams. Forget about this. This is out. In the standard model, you can draw a 4-point diagram like this. You can draw diagrams mediated by the Z or the photon. And then you can also draw the diagrams mediated by a Higgs boson. So you have only 5 such diagrams. The important point is that if you do not involve these diagrams, just suppose you have only these diagrams, you want to calculate the amplitude, these amplitudes grow with energy. Now that's a very bad thing. If the amplitudes grow with energy, that is precisely what happens in the Fermi theory. If the amplitudes grow with energy, ultimately you will violate probability conservation and your theory will be non-renormalized. So what happens here is this. Okay. I'm sure you have learned something about scattering. So I can write an amplitude in terms of the partial waves. These are just the partial waves. And you can show that these partial waves, here we will need only 3 partial waves, 0, 1, and 2. These partial waves have a form like this. This is the energy. So this is some q to the power 4, energy to the power 4, energy square, and some constant. This 8 q to the power 4 term, they cancel between the gauge diagrams. I mean diagrams involving W, photon and Z. But if you want to cancel this term, the q square term, you need the Higgs. This was shown in a famous paper by Lee Kuiger and Thacker. This is the Benjamin Lee that I was talking about. Okay. So that's a very good point. It does not only give mass to the gauge bosons and the fermions, it also makes the standard model a denormalizable theory where you can do the calculations in a meaningful way. The only unfortunate part is that this does not predict the mass of the Higgs boson. So we have to search for a needle in a haystack. And that is precisely what the LHC did. This is the LHC tunnel. I'm sure you have all seen the picture of this. This is a tunnel with a circumference of 27 kilometers. And this is a perfect circle. So forget about physics, everything. Just think of the engineering and sitting in a country where you have water logging on the top of a flyover. You just think of the engineering here. This is a perfect circle that goes under the Geneva Lake and under the Jura Mountain. I mean, Geneva is not beside Alps. This is beside another mountain range, which is called Jura. And this gave its name to one of the geological periods. It's called the Jurassic period. Okay, so in this tunnel, there are two proton beams going like this, and they collide at some fixed points, and people see what comes out of this collision, because proton is not just like these two upwards and a downwards. That is what is told in your undergraduate textbooks, but that is not correct. It is actually like a big ball of quarks, antiquarks, and these gluons, which keep these quarks and antiquarks together inside the proton. So when two protons collide, these balls just get smashed, everything comes out, and people are looking at what are coming out. So there are two major collaborations here. One is CMS, one is Atlas. There are lots and lots of Indian collaborations, Indian groups in CMS. And there are two more specific experiments. One is called ALICE, the other is called LHCb. So what these people in Atlas and CMS do, you must have seen that recently they got this breakthrough prize.
The breakthrough prize.
So what these people in Atlas and CMS do is that they look at whatever comes out in the collision of these protons, and they found this Higgs boson. This is extremely unstable. This decays almost as soon as it is created. It decays into two photons. It can decay into a bottom quark and its anti-quark. It can decay into 4 electrons and so on. Okay. This is how it is produced at the LHC. You can have two gluons. Of course, gluons do not directly couple with the Higgs boson, but there can be a top quark going like this. The Higgs coupling is strongest with the top quark. That's why I have taken the top quark. I would have taken any other quark, but the Higgs coupling is strongest for this. This is called
that. Why is it strongest for the top quark?
Oh, because of the mass. Higgs coupling is proportional to the mass.
Okay, so that's
Higgs coupling is just directly proportional to the mass. That's why it is strongest for the top. This is called the gluon-gluon fusion. Then we can have something like this. You have a quark, you have another quark. This radiates a gauge boson. This radiates a gauge boson. Something like the bremsstrahlung, and then they fuse and give rise to a Higgs. This is called the vector boson fusion. You can have something like this, a quark and an antiquark, giving rise to a gauge boson, which goes to say another gauge boson and a Higgs. This is called the associated production. And you can also have something like this, a top quark, a top and its antiquark, and the Higgs coming out of this. Okay, it could have come out of this leg or this leg. This is called the TT by H production. The gluon-gluon fusion is the dominant mode. This is almost 85%, and this is 110, and they are much smaller. The collision energy, I mean the total energy of this a proton on this side and a proton on this side is 13 TeV. In fact, this has recently been upgraded to 13.6. 1 TeV is 1000 GeV, that is 1000 times the mass of the proton. So these protons are completely relativistic. Okay. So the question is, we have found something, but whether it is really the standard model Higgs. I am not going to explain in all details for this slide, but we will define this ratio. Suppose this is the guy that we have found experimentally. Let me call this H125. Whether this is the H standard model. So for that, we will just check the ratio of the couplings with say fermion-antifermion pair or the gauge bosons. So we have different kappas. Kappa W means the strength of H125 is W plus W minus divided by the predicted strength in the standard model and so on. And see that they are all consistent with 1. Each and every one is consistent with 1. So we are more or less sure that this is the standard model thing. And we have completed the standard model. Okay. So now I will come to the second part, the unanswered questions, but I have already taken a lot of time, so I may not be able to touch all. Fine. The first question that is still unanswered is why the Higgs is at 125 GeV and not at the Planck scale. Now, if I ask this question, you might say that why it should be at the Planck scale, everything else is at the electroweak scale, the weak gauge bosons, they are 80 GeV or 90 GeV, the fermions, even the heaviest fermion, the top quark is 174 GeV. So why should the Higgs boson be at the Planck scale and not at 125 GeV? I will show you why. But let us first define what I mean by fine tuning. Suppose I have some parameter, some quantity A, which I found as a sum of two quantities B and C. Suppose you change B by a small amount, delta B, which changes A to A plus delta A. Now, if it turns out that delta A by A is much greater than delta B by B, then I will call this a case of fine tuning. Let me give you an example. Suppose B is 10,000 and C is minus 9,999, so that A is 1. Now, if you change B by say half, then delta B by B is half divided by 10,000. That's a small number, but delta A by A will be half divided by 1, which is half. So, this is a case of fine tuning. Now, the fermion and the gauge boson masses. Fermion masses are of this form, some mass times psi by psi, and gauge boson masses are of this form. They are protected by some symmetries. Fermion masses are protected by what is known as the chiral symmetry. I am not going to tell you what that is, but just take it from me that that is some symmetry of quantum field theory that tells you that even if you do some quantum correction to the fermion masses, this is at most is logarithmic and is at a manageable level. Similarly, for the gauge, they are protected by gauge. So, if you look at the quantum corrections, which are also known as radiative corrections, they are of this form where lambda is some high scale, maybe the Planck scale, which is 10 to the power 19 GeV, but this is log of that. So, this is not a very large. On the other hand, this is not protected by any symmetry. This is the mass term for the scalar. And there is absolutely no symmetry in the theory, in the action that protects this mass term. So, if it is not protected by any symmetry, you just calculate the quantum corrections and you will see that the quantum corrections are quadratically divergent. I mean, they come as lambda square, not log of this. Now, let's see what I mean. Suppose this is the Higgs mass. This is not observable, but I add the quantum corrections and I get the physical Higgs. This is 10 to the power 4. Higgs is at 100, so this is 10 to the power 4. Lambda is at the Planck scale, so this is 10 to the power 38. So I have two quantities which are of the order of 10 to the power 38, giving rise to something which is 10 to the power 4. This is what I call a fine tuning. The Higgs mass is extremely fine tuned. There is another fine tuning for which you might know that happens in cosmology, and this is called the cosmological fine tuning. Of course, this has nothing to do with cosmological fine tuning, but it is equally bad.
So it's just because you don't have the symmetry protection.
Exactly.
The Higgs field.
Exactly. Okay. So, these are the radiative corrections for the Higgs. This comes from that lambda phi 4 term. So this is proportional to lambda. This comes from the gauge Higgs interaction. This is the top quark loop again, as here. This is relevant because the top quark coupling is the strongest. And if you calculate the correction, these are all of the order of 1. So this correction is of the order of lambda square. And we have a bad fine tuning. Now to tackle that, people have given several genres of theories. For example, maybe there are some other particles whose quantum effects cancel this lambda square. This is the genre called supersymmetry. Of course, we have not found any supersymmetric particles so far. We have not found any partner for the electron. So supersymmetry, even if it is there, it is broken. And the problem still remains. There is another genre where people say that the Planck scale is not that high. Why do you take the Planck scale to be 10 to the power 19 GeV? Maybe it is at 10 to the power 4 GeV, but we are living on one slice of the, maybe the universe is a 5-dimensional object. We are living on one 4-dimensional slice. The gravity lives in another slice, and this is exponentially suppressed. So what we see here is a huge Planck scale, but actually the Planck scale is not that huge. These are known as the extra-dimensional theories, and there are some other models like that. So the only answer is that people still do not have any answer to this. Okay.
Are those extra dimensions linked to the extra dimensions of string theory?
Not necessarily, because these extra-dimensional theories, these people are not so brave as to have 10 or 26 extra dimensions. They are happy with one or two. The string theory people, they never stop at 5 or 6 dimensions. They have at least 10 or 26 or maybe even more. Okay. Okay. Then comes the point of the stability of the electroic vacuum. See that this self-coupling, Higgs self-coupling, this is not a constant in the sense that the electric charge is not a constant. Electric charge, if you know something about quantum field theory, electric charge depends on at which scale you measure this charge. If you measure this electric charge only at a very low energy scale, this gives you something like 1.6 times 10 to the power minus 19 Coulomb. Or if you talk about the fine structure constant, this gives you 1 by 137. We can formulate a differential equation. This is known as a beta function of renormalization group of how this quantity changes with energy. This T in the denominator is log of that energy scale squared. So this is related with energy, and this tells you how this changes. Let us concentrate on these two terms. One is this, and the next one, second one is this. Suppose this lambda is very large. What happens then? This term dominates. If this term dominates, you say that this is a positive term. So lambda will go on increasing and it will soon blow up. It will soon go to infinity. This is called a lambda. Suppose lambda is very small, then this term dominates. But this is a negative term, and it will make lambda negative. But remember that lambda cannot be negative. If lambda becomes negative, the potential goes as lambda 5 to the power 4. This becomes negative. And if the potential becomes negative, it's very bad from a quantum mechanical point of view. You don't have any bound state. You don't have any vacuum. Okay. So the potential has to remain positive, and therefore lambda cannot be less than 0. But if this term dominates, it will pull lambda to a negative. This is how it looks like. This stability depends very crucially on the top mass and the strong coupling constant. This is the strong coupling constant, alpha S, which is analogous to the electromagnetic fine structure. Of course, I have put epsilon 0, h cross c, everything equal to 1. See, this is how lambda goes down. This is how lambda goes down. So, for example, take this line. This tells you that lambda becomes 0 at 10 to the power 10 G. In other words, the vacuum breaks down at 10 to the power 10 G. I cannot take my theory beyond that. If this line is true, maybe it remains as a value theory up to 10 to the power 60. And this tells you that, I mean, these are for different values of the top mass and the strong coupling constant. But this tells you that there must be some other physics intervening. Some other physics intervening if we have to save the vacuum. It looks like this. If Higgs mass is very large, lambda is large. And you hit the Landau pole very hard. If Higgs mass is slightly smaller, you still hit the Landau pole, but at a higher scale. If Higgs mass is very small, your potential becomes unbounded from below. It becomes negative. So, if you really want to be, so this looks like a funnel. And if you really want to move to keep the potential stable up to the Planck scale, you have to be in this region. You have to be in this region.
What is it?
125 is somewhere here. So this is almost like a anthropic principle. I don't like anthropic principle. This is for me, this is a very bad thing. But this looks like a very fishy thing. I mean, almost as fishy as the plots of these Hindi films. Okay.
Lot of coincidences.
Lots of coincidence. So, okay. Oops. Then let's talk about the phase transition. This is something that you people should be more familiar with. We know that the energy density for the CMB photons, they go as 1 over a to the power 4. It's 1 by a cube for the number density, and because of redshift, there's another factor of 1 by a. And the energy density is also proportional to t to the power 4. That's the black body. So T goes as 1 over a, and if we go to the past, and the universe will be hotter and hotter. So if the universe was very hot, the photons can create some particle-antiparticle pair like this. Of course, now the CMB photons can never do that, but in the early universe, it was possible. So we would expect that after the Big Bang, when the particles started to be created, there were equal numbers of particles and antiparticles. But again, we know that this is not true. There must be more baryons than the cosmologists, for some strange reason, call electrons as baryons. That is very bad.
They don't know particle physics.
Of course, because they are ignorant about particle physics, they don't know. So they call electrons baryons. But anyway, electrons are very, very light compared to protons and neutrons. So we can just forgive. The point is that there is an excess of baryons over antibaryons in the universe, and that is very crucial, because that is why we are all here, right? There's no antimatter star, there's no antimatter galaxy, there's no antimatter Ritovan Chatterjee. And this number is also supported from Big Bang nucleosynthesis. So how do I know that there's no antimatter galaxy? Because we have never seen such huge gamma ray bursts. If there is some antimatter galaxy and if that collides with some matter galaxy, you expect some huge gamma ray burst. We have never seen this. We have seen black hole mergers, we have seen these stochastic gravitational waves, but we have never seen any such gamma ray bursts. So we can safely say that there's no such antimatter galaxy. Now you may ask whether some antimatter can survive the annihilation because the universe inflated. Technically, yes, but then you can calculate this and you know that this is of the order of 10 to the power minus 20. So this cannot explain the baryonness. And the last alternative is whether the universe started with a baryon asymmetry. It's not really very feasible. And even if it started, it would have been diluted by inflation. Okay. Okay, so we do not know the mechanism that created this barrier asymmetry, but we know the necessary conditions that for a non-zero barrier asymmetry. These are known as the sum of conditions. The first one is that there must be some barrier number violating interactions, obviously, because you start from a zero barrier number only photon bath and you create some barriers asymmetry. So there must be some barrier number violating interactions. Charge conjugation and this combined charge conjugation and parity, these symmetries must be violated, or you will have equal number of quarks and antiquarks. Again, that will lead to zero barrier asymmetry. And this interaction must proceed out of thermal equilibrium. That is, only the forward process can be there and not the back process, because otherwise the barrier asymmetry will be washed out. Now, remember that we are talking about some electroweak phase transition. In the early universe, very early universe, it was very energetic and the electroweak symmetry was exact. The field was, the potential looked like this. Remember that now I have to take into account the finite temperature effects, right? Because we are talking about a hot universe, so we have to take into account the finite temperature. Now, even if the potential looks like this, as the temperature goes down, the form of the potential changes. And once it goes past the critical temperature, this is no longer the true vacuum. The true vacuum comes here, so the universe rolls down here, the symmetry is broken, the Higgs mechanism is complete, and gauge bosons and fermions get their masses. Now, this change can be like this or like a smooth. This is like a bump, this is a smooth thing. This is a first order phase transition. This is a second order phase transition. Of course, the vacuum expectation value is the order parameter. The question is whether it is a first order or a second. We need a first order. We need a first order because the second order phase transition washes out the asymmetry. We need a first order phase transition, but how do I calculate the order of the phase transition? For the standard model, it is very easy because you know all the masses. You know all the masses, so you know the correction to the potential, and from that you can calculate the order of the phase transition. This depends on the Higgs mass, this depends on the top quark mass. And in the standard model, this is definitely a second. There's no way you can make it. Okay. So these are the lessons from baryogenesis. First one is that we do not have a mechanism to create this barrier asymmetry in the first place. Forget about the washing. To create this barrier asymmetry, we need the violation of both C and CP. In the standard model, there is a mechanism for CP violation. In the standard model, there is a mechanism, but the amount of CP violation that this mechanism produces is very small. Of course, this has been tested in lots of experiments, and we know that this holds. This mechanism, this is called the Kavibo-Kobayashi-Maskawa mechanism. I am not going to describe what it is, but this depends on the existence of 3 generations of quarks. And we know that this mechanism holds. But at the same time, if you calculate the barrier asymmetry, this comes out to be of the order of 10 to the power minus 18. It's not a factor of 2 or 4. It's a billion times smaller than what is observed. So you know that there is some new physics. There has to be some new physics that gives rise to this barrier asymmetry. And then you want to preserve this asymmetry. To get out of the thermal equilibrium, you need a first order phase transition, and the standard model is only second. So maybe you have more scalars. You have brothers and sisters of this Higgs boson. What happens if you have more scalars? You can make the phase transition first order. That's a very good. They come from the new couplings, self-couplings of these Higgs bosons. And interestingly, if you have more such things, this can give rise to a stochastic gravitational wave. If you have more scalars, this can give rise to new source of CP violation, so that this need not be the only thing. If you have more scalars, you can maybe the potential does not become that negative. If you remember that the scalars try to lift the coupling up, so you can make the potential stable up to the Planck scale. And there are many such models where these new scalars can provide some cold dark matter candidate, like some singlets or what is known as the inert to Higgs doublet model. They can even generate the neutrino mass. Remember that the neutrinos have a small mass. They can even generate the neutrino mass through the seesaw mechanism. And of course, there are models like the supersymmetric models, which need more Higgses to just for their formulation. Remember, the supersymmetry needs at least 2 such Higgs doublets for a consistent formulation. Okay. So this is my last slide, whether there are more scalars. And now I will give you a good news. There's nothing confirmed, but there are some very strong hints, very strong hints. If you have not heard them before, take it from me, and maybe 2 years from now, when some of them are confirmed, you should thank me. Okay. The first one is one at 95 GeV. Let me call this H95. People have seen them decaying into 2 photons, tau plus tau minus, and some associated decay channel. Now see that there are 2 columns here. One is called local significance and one is called global significance. I should tell you what they mean. You look at what is expected in the standard, and then you look for some bumps, whether there are some excesses over the standard. Now, if you have a bump, you calculate how significant that bump is. So you calculate some ratio of signal divided by square root of background. And if it is a Gaussian, normalized Gaussian distribution, this tells you how much sigma this is. But remember that this bump can be anywhere. Let me give you an example. You know that there are many rare diseases, very rare diseases. Suppose there are 100 such rare diseases, and the probability that someone will have such a disease is 1 in, say, 1 million, 1 in 10 to the power 6. That is, if you survey 1 million people, one of them should have, say, some disease A. But there are 100 of such diseases. So, what is the probability that someone will have at least one of these diseases? That is not 1 in a million. That is much more, right? We are looking at a bump. We are looking at some excess. So it could have come here. It could have come here. It could have come there. Just because I have found an excess, there's no reason to jump and say that, I have found something great. I mean, this can be just some statistical fluctuation, which would have occurred here or could have occurred there. And that reduces the global significance compared to the local significance. So we should look at this global significance. And you know how to combine this significances. So if you look at the significance for H95, this is about 3 sigma. There is another bump at 650 GeV, which is produced mostly through vector boson fusion. This is 4 sigma. Even if you combine the global significances, this is 4 sigma. Remember that 3 sigma is interesting. 3 sigma means the probable that this is statistical fluctuation is only 1%. But particle physicists are very conservative, and that's why they would like to have it at the 5 sigma level. This is not yet 5 sigma. And there is another object at 400. Some people say that this is at 350. This is a TT bar bound state. which has a significance of just more than 3 sigma. And there are also claims of another scalar, which is at 150 G. So
These
they
are all in LHC or other?
all at LHC, all at LHC. No other experiment can look at these things. These are all at the LHC. Lab is already closed. Lab is already closed because this one actually came from lab, but lab is already closed. All the other numbers are from LHC. So all these references, this is taken from one of our papers, and these references are all from either CMS or. So the situation is not that bleak. That's what I would like to tell you, that there might be more such scalars, and they might lead to the answer of a lot of unanswered questions. So let's again take stock. We have the fine-tuning problem, we have the baryon asymmetry, we have, the generation of the asymmetry, the prevention of washing out, then we have the stability of the potential, we have the dark matter. Okay, and you can always think of SIP. Of course, SIP is the creation of that asymmetry. You have to create that asymmetry, then you have to preserve this asymmetry. Right? So there are lots and lots of things, and maybe we should have some answer maybe in a couple of years. Okay, so that's all. Thank you.
Okay, questions? Yes.
Sir, we are calling particles and scalar and vector, like vector Boson, scalar Boson. So what does this signify?
Oh, this is essentially the spin. About the spin. See, particles have, this spin is some sort of an intrinsic angular moment. Just like electrons have spin half, photons have spin 1, they are called vectors. Objects with spin 0 are called scalars. Now that's a very good question, because Higgs boson is the only elementary scalar that we know. All the other spin 0 objects, whether they are pi mesons or whether they are Cooper pairs, they are all composite objects. Some fermion, anti-fermion pair. Higgs boson is, as far as we know, is the only elementary scalar, spin 0. Yes, I should have said that. This is spin 0.
Other questions, Mashalji?
As you showed that Higgs boson leads to gamma rays. Now, can the Higgs boson be created in the astrophysical sources where photons are accelerated to extremely high energy?
See, the part is that Higgs boson is extremely unstable. When you talk about Higgs that you see in the sky, you essentially talk about stable objects. That's why you have electrons and protons and neutrinos like this. Higgs boson is a very unstable object.
But is there possibly like high energy proton condition?
No, sir. So, what exactly is your question?
Question is that if you see high energy.
No. Let me get from her.
Okay.
So from the high energy proton condition, then can Higgs boson be created, and thus the gamma rays?
See, that Higgs boson can always be created in a high energy proton condition. The Higgs mass is 125 G. So the components of the proton that come and collide, they should have that energy. So if you calculate the total energy of two protons should be of the order of 1 T. I am not really very sure about how much energy you get in astrophysical sources, but probably you get that amount of energy. Yes. Now, say if two such high energy cosmic ray protons collide, you can theoretically produce everything, that including Higgs boson. The only part is that the probability that you will produce a Higgs boson is very small, is extremely small. So, for example, when we are talking about Higgs bosons produced at the LHC, these bunches have billions and billions of protons colliding with each other. Right? If you just have one proton colliding with another proton coming at very high energy, the chances are almost zero that it will answer. Right? It also depends on the probability. But that's a good question. Thank you. Yes.
What is the scale of the gamma ray burst if some antimatter and matter collided? You talked about.
Let's see. Suppose you have some protons annihilating with antiprotons. Proton has a mass of 1 GeV. So I would expect these photons to be of say 1 GeV energy.
Other questions?
There might be attenuations, there might be other factors, but it should be of the order of 1 GeV.
Or only one proton and
I mean, if one proton annihilates with one antiproton, they will give rise to 2 photons, right? They cannot give rise to 1 photon. They will give rise to 2 photons. So the energy will be shared, and one photon, a single photon will have something like 1 GeV. So that's a gamma ray photon.
Abhijit has another question, but if anyone has questions, then I'll. Yes.
Yes. Equal interaction of what? No, the equal interaction is there.
Will be there, but then what will be the masses is
Masses of what? No, sorry. Sorry, what is the question?
No, the question is that another scalar is there.
Oh, okay.
Then again, we can have a
Fine.
potential like that. Yes.
First of all, you have to see whether that scalar has a vacuum.
Yeah.
I mean, you can have scalars without a vacuum. Suppose this is a vacuum. Fine. So the Fermion masses will have contribution from that, and that tells you that the Fermion mass matrix and the Yuga matrix will no longer be proportional to each other. But that is something that happens even in 2 weeks later.
Yeah.
Okay, other questions? Yes, Kiran.
I have 2 questions. The first is probably related to this, that if you have this multi-scalar, multi-fields, like multi-scalar representing the Higgs thing.
Yeah.
So does it not have any effect on the spontaneous symmetry breaking and the Higgs mechanism and the giving
No,
of-
I mean, for example, even with a more complicated Higgs structure,
Yeah.
you can have this spontaneous symmetry. If you have only a single doublet, what happens is that your Yukawa matrix, I mean the fermion, antifermion, Higgs complex, that is directly proportional to the fermion mass. Once you have a more complicated structure, that direct proportionality is no longer valid. But you can still have a Higgs mechanism. For example, if you have 2 doublets, there will be 8 fields. And once you have this Higgs mechanism, few of them will be absorbed by the gauge bosons, and 5 scalars will remain. So you should have 5 scalars. 2 of them will be charged, and 2 of them will be neutral.
So does it have any effect on next to the mass hierarchy? So we have this mass hierarchy issue in part standard model, right? So does it have is there any way that we can connect them with that? Like why the electrons
No, sorry. You mean why the electron is so light and the top quark is so heavy? No, this will probably not help unless you can relate this with some sort of a symmetry that acts between the generations. This is called a horizontal symmetry. And it's something that relates the electrons with the muons and the muons with the taus, and then breaks, and say the 3rd generation objects get mass and the 1st and 2nd generation objects get their masses from radiative directions, and that's why they're small, things like that. That's sort of a more complicated. Yes. Yes.
So you said that finding the Higgs boson in the first place was problematic because we know the mass of the Higgs, and it was very difficult problem to find
Yes.
Dirichlet problem.
Yes.
But then these scalar, the new scalar bosons that you told in the last slide. So they so here are all the channels known and we know where to look, or again it's another just finding many individuals in the Higgs kind of a problem.
it is always finding a needle in the haystack. But now, of course, you know how the haystack looks. For example, you are looking at, say, final states where you have two photons. You know that Higgs boson can decay into two photons, of course, not directly, but through some quantum correction. And so if you look at, say, final state with two photons, you will see that above the standard model background, there is a peak at 125 G. And that tells you that there is something new there. Similarly, if you look at this process, you will see that there are other bumps at other points. Okay, so you think that this might be interesting. And if you look at some other channel and you find the same bump, then you will be more excited.
Other question?
But it is always looking in a haystack. We do not know the masses, so I mean we have to search everywhere. I mean it's not just like looking under the lamppost.
So here,
Oh. Yes.
so here the form of the potentials are very. How do we get to the mass?
Form of the potentials are not important. You know some basic characteristics of the potential. For example, if it is more than 5 degrees, it is not a non-negative. You would like to have it. So whatever we have.